On this worksheet, we're going to be looking at the mechanisms for adding an electrophile to a benzene ring that already has a substituent present. We're going to start by just taking a refresher, just looking at the nitration of a plain benzene ring. So this would be adding a nitro group to a benzene ring. This is the electrophilic aromatic substitution mechanism, and I just want to remind you that this mechanism would be exactly the same regardless of which electrophile we're using here. So even though I'm showing the nitro electrophile, no matter what electrophile we use, it'll look exactly the same way. In this mechanism, one of the electrons from one of the double bonds is going to attack the electrophile to create a carbocation intermediate. That carbocation intermediate has two resonance structures. Together we call all of these the sigma complex. And then at the very end of the reaction, we use some sort of base, which for some reason I'm not showing anywhere on this worksheet. We use some sort of base to abstract that hydrogen from the benzene ring to give us our product, which is aromatic. So what we want to consider in this worksheet is how would the reaction be different if the benzene ring already had a substituent present? For example, to start with, we're going to be considering the nitration of toluene, a benzene ring that has a methyl group present. And again, I want to emphasize that I'm just choosing to use the nitration reaction, but no matter what electrophile we would be using in this reaction, our answers to these questions are going to be exactly the same. So we want to be focusing on two specific things here. We want to be focusing, number one, on where will that new electrophile go on the ring. Nitro group in this case, but whatever electrophile we're using, where will it go? By that I mean relative to the existing substituent. We have a methyl group already, so will our new electrophile go to one of the ortho positions, or will the new electrophile go to one of the meta positions, or will it go to the para position? And then the second thing we want to think about is, will the reaction be faster or slower than the nitration of just plain old benzene? So having this methyl group on the ring, will it help the reaction take place, or will it slow the reaction down and make it less favorable? And to answer these questions, we're going to be looking at the mechanism of the reaction considering all three possible locations of that incoming electrophile. So we want to consider the possibility that it goes to an ortho position, we want to consider the possibility that it goes to meta, and consider the possibility that it goes para, and each one of those possibilities has its own mechanism. So we've got all three of the mechanisms here to look at. They're all starting the same way. If we're drawing the ortho mechanism, then we want to use one of the sets of double bonds that corresponds to an ortho carbon. So we could use this double bond here, which is what I've chosen to use for the mechanism, or we could use this double bond right here because it also corresponds to an ortho carbon. We're going to use those electrons to attack the nitro group. This is exactly the same mechanism as we would draw if the methyl group wasn't even present. So we get our sigma complex, we draw all of our resonance structures, and then we remove that hydrogen. We end with our ortho product. For the meta reaction, we want to consider the possibility of putting the nitro group in one of the meta positions. So for this mechanism, we could use either this double bond right here because it is associated with this meta position, or we could use this double bond right here because it is associated with this meta position. I'm choosing to use this double bond. Again, same mechanism. We're putting the nitro group in the meta position. We've got all of our sigma complexes, and then there's our product. And then last but not least, we want to consider the para attack. The para position is right here. So the only option we have for using a double bond would be this one right here. It's the only double bond that's associated with the para position. That's going to put our nitro group in the para spot. Same set of resonance structures. Product here at the end. So these mechanisms look a little bit different because they each have the nitro group in a slightly different spot. But in terms of the actual curved arrows and things like that, all three of these mechanisms are pretty similar. So let's go to the next page because we've got a few questions that we're going to answer about this reaction. First question is asking which two of the three mechanisms are similar, what do they have in common? And then we're going to ask which mechanisms are more favorable, which is less favorable. So if you add a second substituent, where will it go? And will it be faster or slower? We're going to go back to the mechanisms to actually answer these questions, so we have them in front of us, so just kind of keep these questions in mind. Starting with, we're going to look for this similarity. Which two mechanisms are similar? And what do they have in common? In terms of, when we're comparing mechanisms and we're thinking about how are they similar, how are they different, we're looking at things like, curved arrows, and we're looking at things like the structures of our intermediates. Now, obviously, all of these mechanisms are different in terms of the positioning of the nitro group. They all have 3 sigma complexes. They all have the same number of curved arrows. They have a lot of similarity in that regard. So what we want to focus on when we're trying to find what they have in common, we want to focus on the actual intermediates themselves, these carbocation intermediates. Are these carbocation intermediates all actually the same, or do they have some slight differences? So I'm circling these positive charges to make it a little bit easier to see. And let's think about these intermediates and what they look like. So starting with our ortho reaction, we've got 2 carbocations in this position right here. And if we look at, and then a 3rd carbocation up here at the top. So if we look at our other mechanisms, try to find some similarity, carbocations down here in the lower left and lower right position, we've got that same set of carbocations down here for the para attack. So these right there, which are the same. And also, take a look at this. Similarity right there as well. In fact, I'm going to use some highlighters. So we could say, look at that structure. In both of these, the carbocation is on the same carbon. The positive charge is on the same carbon that has the methyl group. And then look at this one. Positive charge is in the lower right-hand corner, just like this guy right here. And positive charge is in the lower left-hand corner, just like this guy right here. So these 2 mechanisms have that in common. For the meta attack, all of our carbocation intermediates, they all have the positive charges on carbons that are different from what we see with the ortho and the para. So this question number 1, slide back to this next page. 2 of them have a similarity. Which ones are similar? The ortho mechanism and the para mechanisms are similar, and what do they have in common? What they have in common is the position of the positive charge in their intermediates. So now the next question that we're being asked is, which mechanisms or mechanism is more thermodynamically favorable, which is less thermodynamically favorable? So in terms of what that means, like more or less thermodynamically favorable, more thermodynamically favorable would mean that it's easier in terms of energetics. So that means it's going to have a lower activation energy. It's just easier for that reaction to go. Less favorable, meaning that it would have a higher activation energy. And as a reminder, when we're talking about the activation energy, trying to get up to a transition state or something like that, this has to do, especially in a multi-step reaction, which I should draw it as a multi-step reaction, this has to do with like how much energy does it take to get up to this spot, and that's definitely related to the stability of our intermediates. So a molecule that has a lower activation energy, or a reaction that has a lower activation energy, is one that's going to have more stable intermediate, or it could also have stable products. Higher activation energy would have an unstable or less stable intermediate. Let's go back and take a look at our intermediates. So looking at all of these molecules, and again, we can really just focus on, because we already know that the ortho and the para mechanisms are similar, we can really just focus on ortho and meta, or we could choose to focus on meta and para. Comparing these mechanisms to each other, comparing the intermediates to each other, which intermediates are more stable, less stable. So we're going to use what we know about carbocations, ranking them in terms of stability. And we've got conjugated, isolated. Down here, we've got conjugated, isolated. So they're the same in that regard. We've got an allylic. So they're the same in that regard. We've got secondary carbocation, tertiary carbocation, secondary carbocation. That looks like a 20. I don't know why I drew that circle 2 times. Secondary carbocation. There's our difference. The ortho reaction, one of the intermediates is a tertiary carbocation. In the meta reaction, none of the intermediates are tertiary. Let's just verify that that's also true for para. For para, we have secondary, tertiary, secondary. So yes, because the ortho and the para reactions have a tertiary intermediate, this intermediate is more stable in the ortho and para mechanism, less stable in the meta mechanism. This isn't bad, it's just not as good as tertiary. So how do we answer this question? Which are more thermodynamically favorable? Ortho and para mechanisms are more favorable because of the tertiary carbocation intermediate. Tertiary, I'm getting my notation all weird, tertiary carbocation. And then the meta mechanism is less favorable because it has no tertiary carbocation. So to answer our last question, if we add, or I guess this isn't the last, the next question, if we add a second substituent to the alkylated benzene ring, any kind of alkyl group, like toluene was our example, where will that substituent go? It's going to go into either the ortho position or the para position. And if you add a second substituent, will the reaction be faster or slower? It will actually be faster than putting a substituent on a plain benzene ring. How do we know that? We go all the way back to this regular plain benzene mechanism, secondary, secondary, secondary. So in terms of the plain benzene mechanism is really similar to the meta mechanism in that all the carbocations are secondary. Ortho and para is great because it has a tertiary carbocation.